Hello physics students. So earlier in this topic we defined energy as the ability to do work. And so we then reasoned out that a simple mass can act like a rechargeable battery, storing energy, storing work and then returning it. How? Well, when I lift it, I put in a force times the distance. So I put work in to lift it. And then when I let it go, it hits my hand and it gives me back that work. So I put the work in and then it gives it back. This is like a rechargeable battery, storing energy and releasing. And then we learned that we could do a similar thing with a spring. We could put work in by stretching it. I put force times distance in, and then, so I put energy in, and then when I release, the spring gives back that work or that force times distance. So I put energy in, I get it back, stored energy. Today we're going to learn about another kind of energy, another way you could store work and then retrieve it later. And that's in the motion of an object. And we call that the kinetic energy. So what I have here set up is something that will hopefully allow you to see that. I've got a box over here. And let's suppose I want to slide it across the table or across this board to the side. What I have to obviously do is put work in. I put force times distance, and so I did work to slide the box, positive work. But what if I didn't want to touch the box and I wanted to do it remotely? What I could do is I could incorporate a moving object. This object will not move and will not make the box move unless first I put work into it. So I'm going to put my hand on it and push force times distance in the same direction, putting work in. And then what you'll see is that it'll roll with that amount of work and do work on the box. So, taking a look at that again, watch my hand. It starts here at this sheet of paper, and then I'll put force times distance, so when I push, my hand will move a distance, right? So you see that? It moved from here to here. I put work in, force times distance. And then as that car rolled, once I let it go, it took that work that I put in and it had it in its motion. And then once it hit here, incoming to rest, it delivered that work again, pushed the box from here, force times distance, and returned that work that I put in. So anything moving has energy or work stored in its motion because it can deliver that as it comes to rest later. So let me just move this stuff aside. And that brings us to today's notes. Kinetic energy, that's what that's called. And the symbol we use in Regents is Ke, makes sense, kinetic energy. This diagram illustrates what we saw here. I've got a car at rest. It will not move until I put a force times distance on it. So I'm putting work into the car to get it moving. And then it rolls, the car rolls with work stored in its motion. So it's rolling, that work is in its motion. And then finally when it hits something and comes to rest, the car returns the work it got at the start to the box or whatever it hits. And that amount of work, that amount of energy stored in the motion of an object is given by this formula. Kinetic energy, 1/2 the mass of the object in kilograms times the speed of the object in meters per second. And when you put that in, you're going to get joules. But I want to emphasize again that it's the work, okay, stored in the motion. The work to get something moving, the work that it returns. Because a lot of times, students are thrown off in the Regents when they say, what is the work required to get a 1 kilogram mass moving 3 meters per second? They say, work, force times distance. I don't know the force, I don't know the distance. And they're stuck. And they don't get the answer because they don't realize they're asking for work, but you have to use the kinetic energy formula. You'd be surprised, a lot of people get stuck on that. So remember, it's the work. All right, so if you haven't caught up, then I'll give you a moment to catch up by creating a pause here. All right, so what I'm going to do is a couple examples with this formula, and then we're going to learn yet another formula before we leave today, thermal energy or heat energy. So that's coming up. All right, let's take a look at example 1. We got a baseball moving 30 meters a second, has a kinetic energy of 65 joules. Determine its mass. So we go to the reference table and we find the formula on the test. Of course, we have it right here, but if you are in a test and you need the formula, the kinetic energy formula is on the front cover of the reference table, right here near the back cover, near the bottom of the reference. See, here's the bottom, so a little bit up from the bottom, 1/2 mv squared. There it is. Okay, so we write out the formula. As always, we start with the calculation by writing the formula out. Then we plug in our data, 65, 30, and then when we square this and take a half of that's 450. So I'm going to divide both sides by 450 and I get the mass of the baseball. All right, so let's take a look at another example. But if you need a moment to catch up, I'll create a pause to allow you to catch up. Okay, example 2. Okay, so the car originally has a kinetic energy of 1,000 joules. How much kinetic energy does it have if it moves 3 times as fast? So we don't even know how fast it's moving. We just know that it's going to step on the gas pedal, go 3 times as fast. So this is one of those, I don't even want to say proportion problem, but like a factor problem that I mentioned in the spring potential energy video. The way you figure this out is not with a proportion, because not all things are proportional. Not all things, if you double one thing, you double the other thing. Not always true. So in order to see the pattern, you look up the formula for kinetic energy on your reference table, and it looks like this. And now we could see that the velocity dependence is squared compared to the kinetic energy. So if we triple the velocity, or the speed I should say, then what we're doing is we're making the kinetic energy 3 squared bigger. And 3 squared is 9 times as big. So that's what's happening. We're tripling, squaring, tripling, which is times 9. So the new kinetic energy is 9 times 1,000. Or in other words, the kinetic energy is 9,000 joules. And again, this is not one where you have to show all the work in a nice manner like this example, because it's basically something that would occur in a multiple choice question where you just have to pick the right answer among a bunch of choices. How you get it then doesn't matter. Okay, maybe this makes you uncomfortable looking 3 squared 9 times as much. If that's the case, you could do this. I'll put ALT for an alternative solution. What you could do is you could use the kinetic energy formula. Oops. And I won't write out the formula because this is just kind of like scratch work you would do on a multiple choice. 1,000 joules equals 1/2 m, and then make up a number for the speed. Let's say it's going 1. So basically 1 squared is 1 times 1/2 is 0.5. Divide both sides by 0.5 and I get the mass is equal to 2,000. And then once I have that, I could now use the kinetic energy formula again. 1/2, 2,000. And triple the speed is 3. And what I get is 9,000 again. So you see how it's more calculating, more effort to get the answer this way. But again, if that's what it takes for you to get the right answer, then do it and get the right answer. All right, so there's another example. If you need a moment, I'll create a pause to allow you to catch up. Okay, so the next example, let's suppose you have to sketch the graphs, and I won't write it out. Oh, no question mark. Write out the question in nice detail because I think it'll be obvious here. I create some axes like this, and let's suppose I do kinetic energy and mass on this axis and kinetic energy versus speed on this axis. And again, you don't guess, you don't memorize. What you do when you're confronted with a graph question on the Regents is you always go to the reference table, find the formula, and it will tell you the pattern. Like, for example, the first one we could do is see we got the v squared. That's like x squared. That tells me if I plot kinetic energy versus v, it's a squared pattern or a parabola. Okay. The mass dependence, though, this is like to the 1 power. So it's like y equals x to the 1 power. And there's no squared on the mass term or to the cube power. So that is a straight linear line. You double the mass, you have double the kinetic energy. You double the speed, you have quadruple the kinetic energy. This explains why speeding, you know, in driver's ed, or your parents might lecture you a lot about speeding because we'll see in the calculation later in this topic that if you go twice as fast, you're going to have 4 times as much kinetic energy. It'll take you 4 times the distance to stop. If you go 3 times as fast, you have 9 times the kinetic energy, as we just saw. It'll take you 9 times the distance to stop. And if there's a hazard in the way, you might not be able to stop in time or in small enough distance, and you might end up crashing. Speed is very difficult to control, more than mass, okay? Worse than having a lot of people in the car is going too fast in terms of stopping. So that's just a little aside. All right, so let's go do the final energy for today. Okay, if you need a moment, I'll create a pause in case you need a moment to catch up. Okay, last energy. Heat energy. The symbol we're going to use is Q for heat energy. The formula is this. The heat Now, before I explain what this means, I'm just going to tell you that you will not find this on the reference table anywhere in any of the pages because this formula is not in the curriculum. So it will not be on the Regents. I'm showing you the formula because we're going to be doing a lab later in the year that involves heating up water with electricity. And what we're going to be doing is we're going to have to determine how much energy the water absorbed based on how much electrical energy went into it. And so if we don't have this formula, we won't be able to do the lab. So we'll learn it here with the energy unit so we could use it later. So what do all these variables mean? C is called something called the specific heat. And the reason why we need it in the formula is because not all things take the same amount of heat to raise the temperature. For example, if you try and heat up water, it takes a lot of energy compared to something like a piece of plastic, even gram for gram. Water takes a lot of energy, so we need a term here that factors in whether you're heating water, plastic, metal, glass, whatever it is, all takes different amounts of energy to raise it up a certain temperature. So the specific heat for water is actually 4.16 joules per gram per degree Celsius. And yes, I did put mass in grams. This is the only formula all year where you're going to be using grams. Every other formula in physics, mass has to be in kilograms. But just in this one, you plug it in grams. And then delta T is the change in temperature. And that's going to be in either degrees Celsius or degrees Kelvin. Okay. So that's the heat. So you take how much water, maybe like a glass of water, a big glass of water could be 500 grams here, 4.16 for water here, and then how much do you want to heat it? Maybe you want to go from ice cold water, maybe it's like 0 degrees Celsius, and then you want to heat it up so it's like a comfortable bath, and I don't know what that would be, like maybe 25 degrees Celsius. So your delta T would be 0 to 25 degrees Celsius there. And that's how you plug everything and calculate. But I'm not going to do an example. There is one in the homework. I'll see if you could figure it out. So that's it for today. We learned kinetic energy. That's the big one. That's one you want to focus on with your studying because that's heavy in the Regents and important for the rest of the topic. What it is it's the amount of work you put into something to get it moving. And then when it hits something and comes to rest, it gives that work back. The amount of kinetic energy is Ke equals 1/2 mv squared. Don't worry about memorizing the formula. It's on the reference table. And then, of course, we got graphical, conceptual examples, numerical examples that you're going to practice on the homework. All right, I hope you enjoyed the physics video today. I'll see you in the next physics video.